Hello, it's a pleasure to present to you all the uh, program that I've been working on for this past summer, and it's on theories of neural plasticity and learning. So, a brief overview of what we'll be discussing today is a bit of a background on single neuron layer networks, where we'll discuss batch gradient descent or offline OHS algorithm, online OHS algorithm, a discussion of momentum and accelerated gradient methods, and a brief introduction to multi-neuron layer networks. So I'd like to start off with a comparison between artificial neurons used in neural networks and biological neurons found in the human brain and other brains. Essentially, we'd like to make the analogy that neurons will receive input from a variety of sources, and these can be represented with a data vector X or matrix X, and they will normally compute an output that we can represent with a scalar Y, or in the case of multi-neuron layer networks, a vector Y. We say that the synaptic strength between neurons can be represented with either a vector W or a matrix W, depending on if you're working with a single neuron layer or a multi-neuron postsynaptic layer. So a brief overview on necessarily what we are essentially testing. So machines essentially learn by minimizing some cost function, where this cost function is a measure of how effectively the machine can compute a given learning task. And one way it minimizes this cost function is adjusting a variety of parameters using a method called gradient descent. And in gradient descent, we essentially move in the opposite direction of our computed gradient, and we can adjust how fastly we do that using what's called a learning rate. And practically speaking, we say that this gradient is dependent on our weight matrix for the discussion of neural plasticity. And so we start off with one principle on algorithms for neural plasticity that states that neurons that fire together wire together. This began in 1949 with the publishing of Donald Help's Organization of Behavior, in which he essentially states that the synaptic strength between two given neurons are dependent on if they fire together. And so using this principle, we'd like to take existing machine learning algorithms and apply some biological constraints to them to elucidate possible mechanisms of neural computation in the brain. And some biological constraints that we apply are that we normally would like to work with online algorithms. The contrast to that are offline algorithms that utilize a whole data matrix instead of a single data vector at one time. We think of how the brain receives information, which it does sequentially. It doesn't take in big batches of information. We state that updates to the synaptic strength between two neurons or the weight of the neurons are dependent only on the activity of the presynaptic and postsynaptic neurons. The idea being that if you have that the synaptic strength between two neurons aren't dependent on what some faraway neuron is doing. And we generally work with unsupervised algorithms simply because the brain oftentimes doesn't work with very neatly labeled data sets. And so we go into a brief overview of single neuron layer algorithms. The first one is OHS algorithm. It, I believe, was published in the 1980s, and it essentially states that neurons do some form of principal component analysis, which is used in dimensionality reduction by essentially taking vectors of a data matrix that best explain, that have the highest covariance, which is a measure of how well it can essentially explain the phenomena going on in the matrix. And from the cost function shown on the screen here, you're able to derive update functions for the weights or the synaptic strengths of neurons. And so we looked at the offline version of this algorithm, which, as you can see, compared to the online version, has less stochasticity. This version here is, as we said, not very biologically plausible because it's an offline algorithm and we don't believe the brain works in batches. Whereas here, it is an online algorithm, but we notice that it has more stochasticity and it takes in, like we said, one data input at a time. You'll see that the difference between the two plots is one of big eta, so it moves very, it makes decisions very quickly, versus here with small eta, so the model learns relatively slowly. And we'd like to do a brief discussion of momentum and accelerated gradient methods, where these are essentially additive terms you can use in your model to make it reach its optimal solution relatively faster or with more stability. And so we discuss the momentum term, which essentially adds to a given weight update the result of the previous update scaled by some scalar between 0 and 1, commonly 0.9, and accelerated gradient, which essentially the weight update is computed at a position that should be somewhere in the future. So it sort of predicts the gradient at a position where it predicts it will be next. And we can see the performance of all of these algorithms. The online algorithm is shown above, and we'll see that compared to its non-momentum or non-accelerated gradient methods, it performs very well in terms of reaching a relatively low error sooner. And for the offline version, we see similar behavior. And so we move on to multi-neuron layer algorithms. And the first thing I'd like to discuss is similarity matching, which is normally used in a data analysis technique called multi-dimensional scaling. And the idea is that, like OHA's algorithm, it performs principal component analysis or dimensionality reduction up to a rotation, which essentially means that if you rotated your principal components, they will be as if you had computed regular principal component analysis. And so this is the associated cost function. From this cost function, we can derive our update terms. And our update terms, we notice that we have two, where we introduce the M matrix, which essentially explains lateral connections between neurons in the same layer. And like beforehand, we test our algorithm in the offline setting and notice decreased stochasticity. If you're interested, we have the exact algorithm used here right below the text. Same with the online similarity matching, and we notice the increased stochasticity, and we see that as before, the momentum method performs better than the non-momentum method, and the Nestor's accelerated gradient performs the best, as to be expected. And so we'd actually never, my researcher had never encountered similarity matching with these additional terms. And so one of the things we were responsible for was hyperparameter optimization, particularly for the gammas, which are related to the M matrix. And so we found out that a higher gamma typically is best to have. And future avenues of research that I'd like to approach, I think most interestingly, how we can use single neuron dynamic simulations to confirm our theories of neuroplasticity here are interesting. And finally, I'd like to thank the following people for making this program possible and for just in general making it a pretty enjoyable experience. And, yes.
Use your seat mic, please.
Oh, your seat mic? It's the black button.
That works. Wow, something works. Okay. Okay, so there seems to be some analogy with mechanics here. So what is the sort of physical intuition that I should have when I think about this velocity vector as a way of modifying the weights?
So from what I've read, the way to think about it is that as you roll down a hill, you normally build some momentum. And so if you think of your cost function as defining surface, as you go down that cost function, you'll build up some momentum. So the momentum term is essentially trying to reconcile those two concepts.
So the momentum term looks a lot like the Hamiltonian Monte Carlo method kind of term.
Gotcha.
Where you're making, use of sort of a Hamiltonian to describe the dynamics of the system. So, I mean, this would mean that the neurons preserve information on the previous update.
And so that's like one of the reasons why I'd like to learn more about single neuron dynamics is to see if there's any biological basis. For example, I had a question of, is it possible that perhaps neurotransmitters, which operate slower than standard electrical signals, could be responsible for a momentum term being biologically plausible?
So this is something like, my knowledge of neuroscience is very small, but I do know that there are signals transmitted, like there are calcium transmitters, and I think silicon transmitters.
Yes. On different calcium, like pumps and ions.
Right, the pumps with different time scales.
Yes.
So you sort of have built in. I've wondered. I mean, I don't know if this is why, but like our neurons come with two different time scales.
Yes.
In them.
And so, yeah, I think that's an interesting question, and like particularly, I didn't learn a lot about the exact because I really want to know if neurotransmitters can be responsible for like that different time scales so far as the momentum term is concerned. But yes, also considering the fact that the pumps and gates can have different time scales is also an interesting question. Yes.
What are your future plans?
I hope maybe I can join the faculty of Brown University, like one of my big inspirations, and use physical principles like.
You need to first evolve to dreadlocks, then get ready.
That was already the plan. But also, I've seen some people. I know Bill Bialik does some research in using statistical mechanics to explain neural networks. There are some researchers who use information theory. I'm not well versed in information theory, and I am not the best in statistical mechanics. And so if I could learn more about that to explain these theories, that would be pretty cool. That would be, I think, a good life.
All right. So one more question, and then we'll move on.
Did the calculations that you ran use any of the machine learning libraries? So things like PyTorch or TensorFlow?
My mentor wanted me to get a pretty intimate feel for how like these gradient descent algorithms and even like PCA works and similarity matching works. So he had me implement them from the mathematical formulas given.
I agree with your mentor. That's a great idea. Thank you.
Okay, so let's